mostly you'll see the talks posted once they go up, which is pretty exciting.
We have several sponsors that make this evening possible. One of our emerald sponsors is Envato, the world's leading marketplace for creative assets and creative people, and you can find them at envato.com.
Another emerald sponsor is Look Ahead, technical recruiters who are actually technical, lookahead.com.au.
We also have CultureAmp as an emerald sponsor. They are the world's top-ranked employee feedback platform and analytics platform. You can find them at cultureamp.com.
Our venue sponsor, which you may know already, is Zendesk. Zendesk builds software for better customer relationships, zendesk.com. I think you're nodding, that's great. Yes, we do.
And our drink sponsor is Marketplacer, the world's leading marketplace software platform, and you can find them at marketplacer.com.
If you would like to be one of these excellent sponsors, you can get in touch, sponsorship@ruby.org. It's nearly the next financial year, so it's a good time to get involved in sponsoring your friendly local Ruby meetup.
We have a code of conduct which you agree to by coming here tonight. If you haven't read the code of conduct, you can go to this link, ruby.org.au/code of conduct. The short version of it is Matt's is nice, so we are nice.
I like the short version and also the long version. Tonight, we have just one talk. This is a departure from tradition. However, it's like a meaty 40-minute talk, and we thought you'd like pizza in the middle. So that's what we're going for. Do you want to talk about the talk?
Yeah, so it'll be, as Vanessa said, a talk in two parts, presented by Xavier. And the title is Tiny Turing Toys. Did you make me do this on purpose?
No.
Okay, great.
No, it's just how it turned out.
Tapes, states, and breaks.
Yeah. Sorry, it wasn't on purpose. Before we get into that, though, there's a few things to chat about. We've got upcoming events. We have a hack night. You can go and do lots of code with friendly people. They also have pizza there, and it is also excellent. Next Roro, end of next month. And our next Rails camp is bubbling away. We don't have exact dates, but it will be somewhere in Melbourne. If you want to know more about it, or kind of, yes.
Is it like October?
Ish.
Yeah.
Yes. Most
like
likely.
A very stretchy-ish.
Yeah. Yeah, I'd like, you know, October or November. That's a window.
Yeah.
If you'd like to know more about it or give us opinions and ideas, do come and let us know. Cameo and Seals and I are organising. Hiring time.
It's the hiring time. So we start off with an orderly queue.
Yes, but first off in that orderly queue is any of our sponsors who are hiring. So anyone from Envato here who would like to talk about hiring?
Or Look Ahead. Or CultureAmp. Yay!
Hello, I'm not prepared. My name's David Cowan. I work for CultureAmp. I've been there for a couple of years. It's a great company. I like it. You'll like it. We're looking for good people, so come and talk to me.
Thank you, Dave. Zendesk.
I hear you're unprepared and raise you me. I work at Zendesk. We are also good. We are also looking for lots of good people. Sadly, we don't have any junior positions open at the moment because we've just started hiring a whole bunch of new interns. Although I believe we've got an internship program opening up again later this year. But we are looking for lots and lots of mids and seniors from Ruby, JavaScript, data science, you name it, we do it. So yeah, come and have a chat to me or go to zendesk.melbourne to see our open jobs.
Marketplacer.
Okay, anybody else who would like to say that you're hiring?
I also want to talk to this room of fantastic developers.
Yeah.
Where do I work? So apart from doing lots of pairing, lots of testing, and struggling with stage presence. So I suppose what do? We are a platform between restaurants and wholesale fresh food providers in particular. And what our kind of biggest thing that we do is we save chefs about 1 hour a day in ordering, reordering, managing receipts. Currently, chefs are doing that on pieces of paper, sending SMSs, emailing things, etc. We're just a platform that allows them to do that and save them like real time, 1 hour a day for most chefs. We also reduce a lot of waste around food that is or isn't delivered, so it's the right food. Trucks that get sent out, again, we minimise that because a lot of this, because it's ordered online, people know exactly what's going where, when it's going to be delivered, and get the right amounts, etc. So we are reducing a lot of waste by digitising this industry, which hasn't been digitised for a long time. So if you're interested in either that kind of aspirational vision of a company of reducing waste and improving the fresh food industry, or pairing, or testing, or drinking, come talk to me. And then just a last little shout out. If anyone has any developer buddies in Fiji, I'm going to Fiji next week. I'd love to catch up and get away from the family and and have a meet up with somebody. So if you know anyone in Fiji that's a coder that would like to talk to me for an hour or two, tell me.
In the workplace.
You missed a bit.
Thank you, Michael.
That's good. Yeah.
I'll come in at the half time as well.
Yeah.
I'll polish your keyboard.
That'd be perfect. Thank you. Thanks. It's cute.
Hello, my name's Rihanna. I'm at Reinteractive and I'm like 90% sure we're hiring at the moment, so we often are. So we're a Ruby on Rails dev shop, so people come to us and hire us for a few weeks or a few months or something to build them a cool app in Ruby on Rails or to upgrade their existing Ruby on Rails thing to the latest version, stuff like that. So a lot of variety, lot of good stuff there. It is 100% remote, so you work from home. Client work is 4 days a week, and every week you get 1 day of professional development to do what you like, which is really, really awesome and has helped me, really learn a lot more about Ruby on Rails and develop a lot of skills there, which is really cool. So if you want to know more, come find me. Otherwise, it's Reinteractive, so just go to our website and check it out and apply if you feel like it.
Anyone else for hiring? Okay, we can get to... Yes, our talk.
Times.
What's it called again?
I think Vanessa offered to say it a second time.
Tiny Turing toys, tapes, states, and breaks. Yeah. Please welcome Xavier Shay.
Hello. Does that work? You can all hear me? Great. Give me a second to get this set up. All right. Hi, everyone. My name's Xavier. I am from Melbourne originally, but I only just moved back. So I went overseas for 8 years or so. Just got back, so I'm sort of new to the Ruby meetup again, because I used to be part of it before I left. So I'm really looking forward to sort of reconnecting with any of the OGs and meeting all the new people that have joined the community since I got back. So really, it's just such a welcoming community. I'm really proud to be a part of it. This is a talk, Tiny Turing Toys, Tape, States and Breaks. This is a project I've been working on for a little while, and I go into quite a bit of depth on some relatively complicated topics. My goal here isn't to sort of have you leave here thinking, yep, got all of that. It's more to sort of maybe ignite your curiosity. And I've got some things at the end about, maybe other things, if you're interested in this, some other things to look into. So ignite your curiosity and also maybe give you a little bit of a taste of sort of the awe that I've felt in sort of going back through the history of computer science. So that's really what this is about. I work it up with the wonderful humans there. We're building a new digital bank. It's a hip new bank all your friends are talking about. should check it out. We're also hiring. There's a posse of us up the front here. So that's a lot of fun. This talk has absolutely nothing to do with it. So we do need a bit of background. So a little bit of background about me. Who's heard of Magic the Gathering? It's a card game, right? Now, I actually don't play Magic the Gathering, but that's okay. So I've actually got Magic the Gathering is a card game. You have different cards with like different creatures and spells, and they have, like power and toughness. And I'm going to hand around some cards if you just want to, have a bit of a look. There's sort of a set of rules about how to play Magic the Gathering. So pass these around. There you go. Pass them around. Feel free to steal them. And so Magic the Gathering, it's cards, and there's a set of rules that you play. And it's actually quite a fun game, but I don't really play. But one thing I do enjoy doing is puzzles. So you may have seen chess puzzles, right? You got a chessboard, you got a mate in 3. Yeah? Seen those? Some nods, good. You can do the same thing with Magic. You say, all right, well, here's a board set up. Here's the state of the board. How do you win this turn? Well, it's kind of fun. They're kind of hard. I'm not very good at them, but I really enjoy doing them. But I was doing this for a little bit. I was like, oh, well, this is kind of fun, but you know what would be more fun? Writing a computer program to help me solve Magic the Gathering puzzles. So I did that instead. And I spent far more time on this than I have actually doing the puzzles. It's a proof assistant, effectively. It helps you keep track of everything. It's not Ruby code at all. So sorry about that. There'll be some Ruby code later. There'll be a reference to some Ruby code later. But anyway, so that's the background. This is, there's actually not a lot of Ruby in this talk, sorry. But, I did use Ruby for some of it. Anyway, so this is the background about me, right? I enjoy Magic the Gathering puzzles. I have a proof assistant that can assist you with puzzles. Anyway, so that's me. In April of this year, this paper was published called Magic the Gathering is Turing Complete. Now, you may not know what Turing Complete means. That doesn't matter. What it means is Magic the Gathering is a computer. And I thought, hang on, wait, hold on. You can't just go around pointing at things calling them computers. That's not okay, right? A computer needs to be able to run something. A computer needs to be able to compute. So, of course, I thought, well, you're claiming that Magic the Gathering can be a computer. I've got a proof assistant. Surely I should be able to build your computer in my proof assistant. And then I spent a ridiculous amount of time doing that, and this talk is about all of that. So, let's get started. So, it's actually kind of fun. So first we go back to 1937. Alan Turing. Maybe you've heard of him? Kind of a big deal in computer science. Kind of a big deal in beating the Nazis and all sorts of cool stuff. He came up with this idea of a Turing machine. And a Turing machine is sort of a construction. And he said, if you can build it in a computing machine, that's like, it's a computer. Like this is, because when you think about Magic the Gathering as a computer, you need to be like, well, how do you define computer, right? Alan Turing did this, and this is kind of one of the fundamental tenets of computer science. He's like, if you've got a Turing machine, which I'll explain, then you can compute stuff. So, what's a Turing machine? Well, a Turing machine, you start with a big long tape of symbols. Numbers, letters, whatever, doesn't matter, right? Big long tape of symbols, and it's infinite in size. And so on the ends, you sort of have a blank symbol as well. Then you have a little robot, a little read head that can look at the tape, and it looks at the tape and it says, that's number 7. The robot is in a particular state, right? So we've got a tape, we've got a robot, and we've got a state. This state, A, it defines transition rules. The transition rule says when you see a 7, write a new number or write a new symbol, 2, and then move to either the left or the right. Yeah, we'll just move to the right there. Then, and also go to a new state or stay the same. So in this case, stay the same state. Then, oh no, we don't, sorry, forgot. We changed states. We go to state B. Anyway, state B says, oh, okay, well, if you see a 5, then do something else. So we have this infinite tape, a read head, and a transition rule. That's a Turing machine. Now, what we're going to do is, that was a very cursory explanation of a Turing machine, but the best way to understand something is to actually do it. So I'm going to need some volunteers. I need about 5, 6 volunteers. So, yep, 1, 2, 3, 4, 5, 6. Great. You'll need your hands free for this. So I want everybody to line up on the front of the stage here. I need five people lining up along the front. I need one person up the back. You're the tall one, so you're up the back. All right, so you're the robot. You're the reader, and you're either in state A or state B, right? So you start in state A. You can't be in 2. Yeah, that's okay. Now, along here, we've got our ones. Sorry, bit of setup. So 1s and 0s. So you get a 1 and a 0. You're a 1. You get a, oops.
This is good paper.
1 or 0. You need to be a 0. So flip them around. You're a 1 or a 0.
Do I need both?
Yeah, you need both. You don't get. You actually have the most boring job. I'm sorry. You're a blank symbol. So, and then where's my other? Oh, actually, sorry, we got too many. We actually don't need you. I'm sorry.
It's okay.
But
it's all right.
there's another one coming later. So you're first. So what we're going to do, so we've got a tape, yeah? A tape. We've got, so you start above here, A, right? Yep, good. And we have a set of rules. So the way you read this is if we're in state A and we're on a 0, we change it to a 1, we move right, and we change to state B. Yeah? Does that make sense for state B? So, all right, so and this is crowd participation. Right, so we're in state A. What's he looking at? 1. So what do we write? What do we change it to?
0.
Great, good. Yeah, good. Okay, and now, which way does he move?
Left. Your left or my left?
They're left, this way. Yep, good. And what state's he in?
A.
All right, good. Let's do it again, quick. 0. What does he change it to?
1.
Yep, good. What state does he move to?
Right.
Right to B.
And B. Sorry, I got them mixed up. All right, and now one more. Oh, now we're in state B. Tricky, right? We're in a different state. So we're on 0. What do we write? Yep, good. And which direction?
Right.
Yep. And what state?
B.
Good. And now B, blank. What do we do? Oh, we're done. Hooray. Turing machine. Clap, 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 clap. Stay there. Don't move. All right, so we're going to do it once more, really, really quickly. So stay with the numbers, but you reset. So you're now A above him. You stay on 0. Yep, so you're A now. Gotta flip them. Yeah, good.
I don't remember what
We're quickly going to do it one more time.
Turn them around.
One more, yeah, it's fine. All right, so we're in, what state are we in?
A.
What do we read?
0.
What do we write?
1.
Which way does he move?
Right.
All right, and state?
B.
Beautiful. Okay, what are we looking at? State? Hold. Yeah, we got it. I'm going to be stuck. Okay, and we're done. Hooray! Okay, so what is this Turing machine doing? Has anybody figured it out?
Magic the Gathering.
Good guess. Good guess. Wait, somebody said it. Counting. It's every time we run it, it increments a number by 1. That's what this Turing machine is doing. And thank you, everybody. You can take your seats. Round of applause for our volunteers. Very nicely done. I'm very impressed. All right, so every time we run it, it adds 1 to this number. And you might look at that and say, that's not a number, it's 1s and 0s. It's a number in binary. Are people familiar with binary numbers? Mostly, yes. If you're not, I'm sorry, I forgot to prepare an explanation. So I'll help you out in break. But there's a binary number, and every time we run the Turing machine, we add 1 to it. So that's pretty cool. And here is, this is the Ruby portion. I wrote a thing in Ruby that does that. So, hey, Ruby. There'll be more of that coming on. So this is Turing machine, and we can add 1 to a number. So now you can imagine that we can have a different set of states, a different set of rules, and it could do something else. Yeah? So one way to think about Turing machines, right? So this one that I just showed you, it had 2 states and 3 symbols. Blank, 0, and 1 are your 3 symbols, and the 2 states were A and B. So you multiply them together, you get the state symbol product, very technical term, of 6. 2 times 3 equals 6. And this is one way of sort of measuring the size of a Turing machine. It's kind of inexact, but it gives you an idea of how big the Turing machine is. And so now this is where things get interesting. We've got a Turing machine that can add 1, but it can't really do much. That's kind of useless, right? You need a lot more to simulate Magic the Gathering, so how big a Turing machine do you need in order to be able to simulate any other Turing machine? Because if you had this, then you could effectively say, well, okay, I'll write a really, really complicated Turing machine and then simulate it using another Turing machine. It's like writing a VM, right? What's the sort of smallest state symbol product for a universal Turing machine, being a Turing machine that can run any other Turing machine? Anyone guess? Audience participation again, you got to guess. State symbol products, I know nobody has any idea, it doesn't matter. You can't get this wrong. Well, you can get it wrong, but nobody will judge you.
10,000.
10,000, good guess. Any other takers? A million, 6. 50. Okay, all good guesses. The answer is actually really interesting. And we have a fight. This is a fight for the ages between Minsky and Watanabe, two of the great computer scientists of the sort of first generation of computer scientists. These guys, because they thought a lot about this problem, they were right into this. And sort of from about the 60s, because before the 60s, we kind of knew that this was theoretically possible. That's what Turing proved. Turing proved that, yeah, we can make a Turing machine that can simulate any other Turing machine. I don't really know what that Turing machine looks like, but I know it's possible. This is kind of how math works. You sort of like can say slightly ridiculous things and everybody believes you. So that's what Turing said. And everyone's like, oh yeah, cool, that sounds good. But we actually, and then we had a few results or whatever, but in 1960, the first punch was thrown. Watanabe, forgot to have my clicker. Watanabe said 8 states, 6 symbols, 48, got it. Who guessed 50? Yes. Pretty close, pretty close. 10,000, sorry you were wrong, but I appreciate the effort. But then, same year, Minsky shot back and he says, nah, one of those states, don't even need it. 7, 6, 42, too easy. Took a bit of a year, Watanabe strikes back. He said, I'll keep the 8 symbols, I'll drop down to 5 states. 40, it's 2 less, it's even better. Minsky, 62, 6 by 6, don't need any of them. 36, and this is a 1-2 punch, because same paper, actually, just kidding, I can do a 28. Pretty good flex, right? Took Watanabe 10 years, so they had this bad Keras, came back, said, oh, actually I can beat you by 1, 27. How do you like them apples? Rogozin, oh, who's him? We don't know. Comes out of left field. It's like WWE, right? He just comes in with a chair from 4 by 6, 24. And that is currently where we stand as far as the smallest known Turing machine. But there's a twist, right? Because if that's not that's pretty amazing, right? Like 4 states, 6 symbols, you can simulate anything, really? Come on, like that seems ridiculous. But if you sort of relax some of the restrictions of the Turing machine to say, okay, we've got an infinite tape, but rather than it just being an empty symbol, we can sort of generate it using a function, and the Turing machine's actually never going to halt. It's going to run forever. So if you relax some of the minor restrictions, Stephen Wolfram, who's behind Wolfram Alpha, he actually conjectured that a 2-3 Turing machine could be universal. And in 2007, Alex Smith, an undergrad, proved this to be true. So with just a 2-3, somebody guessed 6. You get a prize, which is one of the random magic cards. You can have that. Pretty good prize. It's worth about 2 cents. And Alex Smith, this is just like, this guy, there was a $25,000 prize for proving this. Stephen Wolfram put it up. Rich dude, it's like 25 grand if you prove this. And this undergrad was like, oh, yeah, I don't know much about this, but I can give that a crack. And he did, and it was pretty controversial because, as I said, it's kind of a weakened version, but still, 6. That's insane. We just did a Turing machine that can add 1, and we're like, yes, good job, us. 6 states, 2-3 Turing machine, we can do a lot. We can add 1. It turns out, actually, if we had a different set of rules, we could literally compute anything. How insane is that? Okay, I'm medium levels of insane. Okay, I think this is pretty insane. But anyway, 2-3 is kind of a bit ridiculous. We're going to stick with the Rogozin one tonight. So he came up with a 4-6. This is the rules. I just copied this out of the paper, so it's kind of a bit ugly. But if we're in state Q1, you read a C, write a 0, move right, transition to Q4. Whatever, you don't need to understand that. For various reasons, in the same paper, he also presented a 218 machine, which is also universal. He actually presented like 7. So I don't know, maybe he was just working on this for years. He's just making Turing machines, and then he just dumps them all in a paper. It was great. So this is the Turing machine that we're actually going to use tonight, because this is the one. So if we go back to the Magic the Gathering paper, they said we can make this Turing machine in Magic the Gathering. So that's why we're going to focus on this one, the 218. So, all right, so let's do a concrete example, right? We've got our initial Turing machine that we started with, right? The add 1 machine. Now, we should be able to simulate this Turing machine on this new 218 one, right? Because that's kind of the point, right? The point is this 218 can run any Turing machine, so it should be able to run our Turing machine. Yeah? Make sense? So we know what the symbols of rules are because he gave them to us. So the trick is, how do we encode the symbols, rules, and initial tape of this Turing machine into a tape that we can then run on this Turing machine, right? Does that sort of make sense? That's kind of what we're trying to figure out. Now, okay, turns out there's a few steps. We start with the truth 3. We need to convert it into a machine that only has 2 symbols. Doesn't matter how many states it has, but it can only have 2 symbols for reasons that will become apparent. From there, we need to convert that into a tag 2 machine. We have no idea what that is yet. I was really reading the paper and it says, oh, we'll just use a tag 2 machine. I'm like, I don't know what that is. We'll find out. We'll figure it out. It's fine. Once we have that, we then encode that into this and then profit. So this is our roadmap. This is what we're going to be going through for the rest of the night. But, so we're going to start here. And this first initial process actually came with Claude Shannon in 1956. Claude Shannon, sort of one of the pioneers of, you might have heard of Shannon in relation to information theory. Yeah, I've seen a couple of nods. He also liked Turing machines. He also liked unicycles. He also liked juggling. Pretty cool dude. But we're going to hear more about him after the break because we need to eat some pizza first. So that's part 1. If you didn't like it, you can disappear before part 2. This is the benefit of a 2-part talk. So I'll see you after pizza.
You can probably all see the pizza is here. Maybe just hold back for a second so we can make sure we found the vegetarian ones and like they get them. They'll be on the top.
Easy.
Perfect. We're fine. Go for it. Thank you, Xavier.
Yeah, you got it. The vegan one goes. Yeah. Why are you so old?
Okay, we're ready to rock on with the next exciting installment of
Tiny Turing toys.
Tiny Turing Toys. If everyone could take a seat.
I'm not doing that bit. Tiny Turing toys change breaks and
I don't know. The
A
people
degree
are
in
listening to
STEM is
me.
good for something.
Yes.
Tiny Turing toys change breaks and states.
I would have thought that teaching for a few years would at least get...
Get yourself a last slice or two of pizza and a drink. If you'd like one, come and sit down for the next round of Tiny Turing toys.
Can we do that now or after? I was awkward already.
If you want, sure. All right. All right. 15 seconds. People are getting settled. The microphone's working, I presume? Yep, great.
It is in the front row.
That's all that matters. That's not true. It matters for everybody. I don't know why I said that. Claude Shannon. Welcome back. Hopefully everybody found some pieces they like. Hopefully we're going to drink. Let's get back into it. First, maybe a quick reminder of where we're at. You know, I know it's been 20 minutes. You probably forgot everything. This is what we're trying to do, right? We've got our +1 Turing machine. Everybody remembers that? We had our beautiful humans up the front showing us what that meant. We've got this guy called Rogozin who said, hey, I can simulate that Turing machine in my Turing machine. I've got a virtual machine that can run Turing machines, right? And we're trying to say, okay, sure, but how did that actually work? That's where we're at. That's what we're trying to do. That's what the second half of this talk is going to be about. How do we run this machine inside that machine? We're going to start with this part. How do we get a 2-3 machine into an M2? M, any number. We don't care how many states, as long as it's only got 2 symbols. So Claude Shannon, our juggling unicyclist, he came up with a way to do this. So as a reminder, this is the states and symbols of the +1 adder that we worked with. And another way of sort of looking at this is with this output here. These are equivalent, right? You've got in state A, if you read a 0, write a 1, move right, move to state B. You know, it's just more computery. I put it in Korean New, so you can tell it's a computer. So we've got 4 different rules there. What Shannon realized was like, well, if you've got 3 symbols, you could actually represent those symbols using binary numbers. You just count them up. So I've counted them in a bit of a weird way here, but you can say, okay, this is symbol 0, this is symbol 1, and this is symbol 2. And so you sort of expand out your symbols into 0s and 1s. And in this way, and then you amend your states in such a way to account for this. And so previously where we would read 0, instead what we do is we read 0, we say, okay, we got a 0, but we're not quite sure it's a real 0 yet. Let's move to the right. We've got a 1. Okay, we know that that was a real 0. When you move to the right and you get a 0, you say, oh, actually we're on a blank. Now let's do something different. So by using more states, we can kind of make this work. If you sort of squint, does that kind of make sense? Yeah? All right, so I said that Shannon came up with a method to do this. I didn't actually implement that because I kind of just did it myself because I wanted to try it. And this is what I came up with. This is an automatically compiled, like I gave it the 2-3 machine and said, make this into an M2. And this is the rules that it spat out. And there's quite a few of them. But that's okay, it works. It totally works. I wrote some RSpec and proved that they're equivalent. So that was cool. And that gives us 31 states and 2 symbols. So 62, pretty big, it's fine. It's actually bigger than the machine that can actually run any Turing machine, but that's okay. Shannon actually has a pretty neat algorithm for this that is in the paper that you can read. I just did it for 3 to 2, but he can do it from any number to 2 using the same mechanism. But anyway, so that's pretty inefficient. 31 states, 2 symbols. All of those states are redundant. I actually wrote one by hand, which is this one, which is this is actually, you can sort of see it going along, so we can get a sense of how this works. So we start by reading the least significant bit, and we're in state Q1. There. Then we say, okay, we've read a 1. This is a state name, right? We're in 1. Let's read the most significant bit. And we've read a 1 and a 1, so we know, we just read a real 1. Yeah? So we just read wait on, I read it. Oh, yeah, no, sorry. So we need to set the least significant bit to 0. We need to set the most significant bit to 0. And now we sort of cycle back and we read the LSB. So what we've done here, so this is 1. And now here, we've got a 0 and a blank, because it's part of an empty symbol. And so we sort of keep looping through this Q1 read LSB, Q1 read LSB, Q2 read LSB. So previously this would have been 1 transition. Now it takes us sort of 4 rules to get there. You don't need to understand the detail, but just kind of that general idea of where previously we were just reading it easier. Now it just takes more steps to get to the end. We started with 1, and now we have 1, 0, blank. So we started with 1, and now we have 2. Anyway, this is equivalent to this, which is the same machine that we saw at the start. This is the set of rules for the smaller handcrafted one that I made. So once again, you don't need to understand the rules, just a general idea of we can take this, we can add some extra states, add some extra rule transitions, and we can say, rather than have 3 symbols, now we have 2 symbols. Oops, what was that? The slide is blank on my thing. I forget what it's supposed to be. Well, I copy-pasted an animation, didn't I? Ta-da! Sparkles! Anyway, this is the one that I came up with, which is a 7.2. And you can kind of imagine that, I started with 31.2. With a sufficiently advanced compiler, I could probably get pretty close to this, rather than my shitbox compiler that I just wrote. But this is the one that we're going to use going forward, just because you'll see why. But either way, we're at the point now where we've taken our 2.3 machine and we've turned it into a 7.2, right? Which was kind of the thing that we were trying to do. So we got it, right? That kind of roughly makes sense. Yeah. As I said, we're not going to go through all the details. I just want everybody to get a general sense of what's going on. So, all right. So that's part 1, 2.3 to M2. Nailed it. All right. Part 2. We need to get from M2 into a tag 2 system. But remember, we don't know what a tag 2 system is. So that's part 2A, is what the hell is a tag system? Emil Post, great guy. 1943, middle of the war. Everybody else was fighting the war. He was doing math. He came up with this idea. So he had a Turing machine. And he was like, I have something that is simpler than a Turing machine that I think is pretty cool. I don't really know what it could do, but it's pretty cool. So the way it works is you start with a tape, similar to how we started with a Turing machine. But you don't have a read head, right? You just start at the start, So you read this symbol, and each symbol has a production rule. Production rule says write a series of symbols to the end of the tape. So we read A, we write BBC. That's our production rule. A, BBC. Write it out, Then we drop a certain number of symbols. So a tag 2 system would drop 2 symbols. A tag 3 system would drop 3. Good. A tag 4 system. 4. Good, just checking. All right, so everybody's got that. So we're in a tag 2 system here. That's what we're trying to understand. So we would drop the first 2, and now we repeat, right? Now we just read the B, and we keep going forward. So this feels simpler than a Turing machine, right? There's no left or right. There's no state transitions. It's just a thing, production rule, thing, production rule, thing, production rule. So I'm seeing some nodding. Maybe you've got it, but maybe we need some volunteers to do a human demonstration to make sure that we've really got it. So I'm going to need 5 volunteers. We had the one guy who missed out. get up here. And we need 4 more new people. Don't all volunteer at once. Yep, Mike, get up here. Yep, Chris. Come on, 2 more people. Don't leave me hanging.
Go in the middle.
I can wait here all night. So, this is awkward. Get up here. Pat, good. Yeah, there we go. All right. So, what we're going to do is, now this is going to be a little chaotic because we need to get you all on stage in a row. And Pat, you're going to be the runner. So there you go. You start with an A, and wait on. I'll give you here's a B and a C. But you come over here. You're not in the tape yet. You're in the wings. And now we're going to recycle people. So if you get dropped, you've got to go pick up some more letters because you're going to get on the end, right?
That makes sense.
You get it? Okay, so the way this works, I'll get the extra letters. Okay, the way this works, I put the rules up. So our input, we're going to start with a number, n, right? And we're going to encode this number, because we can't put just a number on here. We're going to take, for every 1, we're going to have 2 A's. So what number is this? Didn't think that made sense. Oh, no, some people got it. It's 2, right? Because we've got 1, 2. You know, if I put 2 more A's on here, we would have... Yeah, great. Okay, you got it. All right, so this is the production rule. The way you read this is if it's A, we append a B. If it's B, we append a C. If it's C, we halt. Yeah? And then we drop 2 characters. Pretty easy one. Yeah? So, we're going to start. What letter do we start with? Okay, so what do we do? Pat, get over there. Go, get there. All right, and then what do we do? Drop 2. So, get out of here. All right. And no, only 2. You're fine. And then shuffle this way. Okay. So now, who wants to be a runner? You can be a runner. There you go. You're next. All right. So now we're looping. Okay. So what do we got? A. So what do we add? B. Get on there. Yep. Great. Okay. Then we get out of here. All right. Shuffle down. Okay. Now it changes. What have we got? So what do we append? C. Mike, get over there. And then what do we do? Okay, get out of here. Now what do we do? Hold. Got it. Okay, everybody done? We're done. Stop. Okay, and now what we do is we count up what's left. How many C's do we have? 1. Great, so we went from 2 to 1. What did we do?
Subtraction.
We subtracted. Great. We actually divided by 2. Same thing. But I didn't want to do it with 8 people to make that really obvious. But so does that kind of make sense? Round of applause. Great. Thank you. Just leave it on the couch. That's fine. All right. So now there is absolutely no doubt in my mind that everybody 100% understands how tag 2 machines work, because they're easier than Turing machines. So that's good. Whew. All right, so this is what we did. A, B, C. Great. Same problem though. So we've got our M2 machine with our symbols and rules and initial tape. This is the 7.2 machine that I came up with. How do we convert that into an equivalent tag 2 set of production rules with A's and B's and C's and all that stuff, right? I don't know. I'll tell you who does know. Mr. Marvin Minsky and Mr. John Cock E? I don't really know the function of that E. But anyway, really smart guy. These two put out a paper in 1963 proving that, basically showing how you could do this. And this proved that if you could have an M2 Turing machine, which we already knew was universal, we didn't know that yet. Anyway, it doesn't matter. They just showed that tag 2 systems can simulate Turing machines, which before we didn't know, but actually it's kind of really non-obvious, right? We've just taken this really simple, like, do a thing, drop 2, do a thing, drop 2. Turns out equivalent in what it can do to a Turing machine, which has the rights and the left and all the states. Like, that's pretty cool, right? Is it cool?
Yeah.
Yeah, great, excellent. Just keeping you awake. So here's the insight here. This here is our Turing machine. It's got 0s and 1s, and the 0s go off forever to infinity, right? And we've got a robot in the middle. So what Minsky and Mr. Koch figured out was that this is kind of a binary number, right? 4 in binary. because you've got, 1, 2, 4, 8, 16. So that's 4. Pretty cool. If you go over the other side, if you sort of flip this around, 1, 2, 4, 8, it's also a binary number. So we've got 2 numbers, 4, 2, and we're in a particular state A. And they thought, well, that's interesting. So rather than having to write out this tape, we can just say A, 4, 2, with some rules about what the 1 is and blah, blah, blah. We'll get there. So let's say the Turing machine moves right. Well, what function does that have? Moves right and writes a 1. Well, now on the left it's a 9, on the right it's a 1. Yeah? So A, 9, 1, sort of equivalent representations. And then B, right 1, move back to the left again. Now 4, 3, B. So this kind of makes sense. We're sort of like encoding this in a state, a 4, and a 3, or a state, left-hand side and a right-hand side number. Yeah, and this is why this is kind of why the 2 symbol thing is important, right? Because if there are other symbols here, then you couldn't really get a binary number out of it. So that's why it was important to get down to the 2 symbols. All right. So what we do is we take this insight and then we say for every combination of state in the Turing machine, moving left or right, and the new symbol that you can write, so 0 or 1, we need a set of symbols and production rules for our tag 2 machine. And so this gets a little bit complicated. I'm just going to move through it relatively quickly. But what we're doing is, this is our tape, right? It's A, we're in state A, 1 on the left, 2 on the right. We've just read something, and we're writing a 1. So this is the end state of our tape. Writing a 1, reading a 0. So we want to go from A12 to A31. Yeah? So, first of all, this is how we encode the initial thing. We have some capital A's just as a constant. Then we have 2 A's for every 1, very similar to what we did at the start. And then we have, that's our left-hand side. Our right-hand side is 2 B's for every B number. Yeah? So similar idea, but with A's and B's. Then the production rules, and these are different depending on whether we're moving right or left. But just, at the moment we're moving right. If we see an A, we go to CC, A, this, B, we write an S, B, we write a single S. You apply those rules and you get to this string. Now, what's interesting about that? Don't all yell out at once, I'll tell you. We've got 6 C's, and so that's kind of like a 3, yeah? It's like, because we've had to multiply by 2 and add 1. So these effectively said multiply by 2 and add 1. It's kind of what this ended up doing. This is the add 1, this is the multiply by 2. On the other side, we've sort of divided by 2, right? We had 2, we've gone to 1, and we had 2, and now we've got 1. So you can kind of see how this is going, right? We've got 1, 2, 3 1s, kind of getting there, pretty cool. Okay, but now we've got these C's, they're not A's, it's useless. Not quite, because our C rules look like this. We sort of just convert the C's into D's and the S's into T's. I don't know why we have these letters. They don't stand for anything. It's just Minsky and John really liked the letters, so that's what we have. But the interesting thing here is the subscript here. So either 1 or a 0, 1 or a 0, 1 or a 0, 1 or a 0. And these are the last 2 steps if you apply those transformation rules to here. And what's interesting is depending on how many C's or S's you have, you either end up on the 0 track or the 1 track. And if you notice this, if we end up on the 0 track, we're always dropping 2. So we're always going to stay on the 0 track. If we end up on the 1 track, we're always going to end up on the 1 track. So this is how, and we can have different production rules for D0 and D1, and T0 and T1. So what this means is whether or not we're sort of, is it writing or reading? I'm blanking. But basically, we can distinguish between a 1 or a 0 based on the previous rules here. This doesn't make any sense until you try and actually work through it for yourself, so I'm just going to move through it. But this is cool. We can have different production rules for the D's and the T's. Production rules here, for this particular set, we're going to write A prime capital for the D and B prime for the T. And now we've kind of looped back around. We've got A, so 3, B, 1. So we've got our 3, 1. We've got our A's and B's. Our A's and B's are what we started with. Except the difference is these aren't the same A and B's we started with. They're a different A or B that represent what state we're in. Because we may have changed states, right? So we may need different production rules. Anyway, this just keeps looping around into different variants of A's and B's and A's and B's. And for every state, direction, and right, we have a different set of rules for A's and B's, so we effectively have a different variant of the production rules. So maybe what you're thinking now is like, wow, that sounds like a lot of production rules. Correct, it's a lot of production rules. So this is a reminder of this. We need 16 symbols for every state, direction, and new symbol. So if we do that, these are the production rules. So we've got A, so what state are we in, what are we writing, what state are we in, what state are we in, what are we reading, what state are we in, what are we reading, and these are all the rules, and there's a lot of them. It keeps going, and wait a second, we're almost there. Yeah, okay, we got to the end, great. So we have 176 different symbols that we need to simulate this Turing machine in a tag 2 system. So you're like, oh, wow, that's a lot of symbols. But if you run the math and you actually try this out, it actually does work. It's pretty cool. Once again, I've written a tag machine in Ruby and I did this and it worked. I was shocked. But technically, we now have the thumbs up for that. We took our M2 system and we have it in this weird tag 2 system that if we run it through, kind of simulates the shifting of the 3s and the 2s and the 2s and the 1s, right? That was probably the most complicated part of the talk. I'm seeing a couple of glazed eyes. Sorry about that. But we're going to move on. We're going to keep trucking through. We've got to get there eventually. So 2, 3, into the M2. The M2 goes into this tag machine. We now have 176 symbols with 176 different production rules. We need to go from here into this machine that Rogozin gave us. So this is the problem that we have. We've got the rules, the 176 rules, and then we have the initial tape, which is the A's and the B's. Yeah? We need to encode those into the initial tape. We already have the symbols and rules. As a reminder, these are the symbols and rules. So how on earth do you encode a set of tag rules and symbols, and tape into this machine? Well, it's quite simple. We'll see how simple it is. So we conceptually, we're into Turing machine land now. So we're back. We had tag machines. Now we're back to Turing machines. Yeah. Our robot sits in the middle. On the left, we have our rules encoded. We number all of our rules from 0 upwards, and then we encode all the rules heading leftwards. We encode all of the symbols on our tape going rightwards, and then we set the machine running, and apparently it all works. So how do we do the rules? We're not going to do the 176 rules because that would be insane. Instead, what I'm going to do is I'm going to take this tag machine, which is the one that we simulated with the humans, and we're going to say, okay, well, can we encode this? We should be able to encode, we can encode any tag 2 machine. This is a tag 2 machine. Let's encode this, right? So we'll do that. First step is you change all the symbols into sequential numbers. So, they're not sequential, incrementing numbers. So you start at 1, and then this is it comes from a paper, so it's math, But you basically say 1, then you add 1 to it, so to get this one, you take this number, you add 1 to it, and then you add the length of how many symbols you're adding. And then you get 3. So we're only adding 1 symbol, so it's 1 plus 1 plus 1 is 3. Here, we're only adding 1 symbol, so it's 1 plus 1 is 6. Halt. And then you rather than appending A or B, you append 3 or 6. It's kind of the idea. So we're taking the symbols and we're just encoding them as numbers. Yeah? Great. Once we've done that, we need to encode these rules into symbols inside the 218 machine. And this looks a little crazy, but so B is a symbol that we have in the machine, right? Because 16 symbols, B is one of them. So we're going to start with 2 B's. Constant. It's just there. We thought it'd be cool. All right. Then we put, following these rules here, you basically, it looks very complicated, but you pretty much do 3 1s, and you just repeat the 1 symbol 3 times. Yeah? All right. Then separator. It's like B is a separator. Yeah? B is a separator. 1, 6 times. Easy. And then halt, we use a Z because why the hell not? So it's actually, in the paper he actually uses like a letter with a Unicode symbol and a thing, but my font didn't support it, so we get a Z instead. Or an S, I'm not really sure. Okay, so if you combine all them together, you smash them all together, that's what our tape looks like. These are the symbols on the tape. We have, rule 2, and they're sort of reversed. So you put rule 0, rule 1, rule 2, rule 3, and we start over here on the right-hand side. Okay, so that's how you encode the rules of any tag 2 system. So we could actually take the 176 rules and go through and apply these things and get some quite large numbers and then get quite a large tape. But the process still works, yeah? All right, so that's the rules. For the initial tape, this part's really easy. This part's great. So now we need to encode the input. So you take the symbol, you find the number. So A was number 1. You repeat 1 that many times, and then you put a C. C is another spacer character. So because our input is A and it's 1, it's actually quite boring. It's just 1C, 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 1C. That represents 4 A's. Line them all up. And then you press go on the 218 machine, and it will totally run that, and you'll end up with a C on the tape at the end of it. C was 6, it'll be 6 1s and a C. And that'll be left on the tape over to the right here. We did it. That's it. So we had this. We had our tag 2 machine. We just showed how we could create a tape to feed into this. So we done? Round of applause? Are we... Well, maybe. I just got up here and, pointed at things and said it was a computer. But, that's what I was skeptical of at the start, right? We actually need to run this thing, right? We actually need to compute something because, I don't know what happens when if I add 1 to 0. I need this machine to tell me. So, I started running into some problems here. So the tag system, the add1 tag system that I showed you was 176 rules. And remember, this was the hand-optimized version of the M2 machine. This wasn't the auto-generated one. So this was me still going in and monkeying with it a little bit. It's 176 rules. So if you encode that using the process that I just described, this is what it looks like. Yep. A lot of 1s. Still a lot of 1s. Keeps going. And then we get to the end. So I know that's way too small for anybody to see, but this here, that's where our read head is. So all of this, these are our tag production rules, and this here is our initial tape. And that's for our add1 system. And so that's about 115,000 characters long on the tape. And that takes quite a while to run. Actually, I haven't been able to run it yet because I left it running for days and it didn't finish. So that's a problem. The generated one, that which is literally we're going from any arbitrary Turing machine, is about 2.3 million. So that's also bad, particularly because the performance character of this thing is severely exponential. So it's not going to take 10x longer. It's going to take exponentially longer. Double it a few times. I don't know. It's going to take ages. So that's bad. And so I was getting pretty despondent at this point. But then I thought, wait a second. The divide 2 tag machine, that we came up and went through, that's only 85 characters long. Cells on the tape. So maybe we can run that. So let's have a look. Oh, actually, no, sorry. And the other problem with this is the tape only gets longer. Because the way the tape works, when we drop 2, you know how I had everybody shuffle down? I only did that because of the camera. In practice, what happens is it drops, and now that's dead space. And then you drop this into dead space, so the machine just keeps writing to the end of the tape and just creating dead space in the middle. So the longer the tape goes on, the more dead space you've got, the longer it takes to run. So it just takes ages. And then, of course, we're not quite finished, because what we're really trying to do is run something in Magic the Gathering, and so actually I've left a bit off the slide. It says, okay, we've got this 218 machine. How do we put that into Magic? That's a different talk. That's even less related to Ruby than this one is. I'm happy to give it, just not tonight, because that's a fascinating topic. But we're not going to do that. But just wave my hands. Also, I encoded the 218 machine in Magic the Gathering, ta-da, and then I ran the Divide 2 tape. I loaded that up into my game of Magic the Gathering, and this here is a trace of the program. So each line is one step of the Turing machine. And I know you can't read this, that's not the point. The general shape, this is the read head over here. And what's cool is you can kind of see the read head going back and forth across the tape. You know, as it sort of reads the production rules, writes some stuff on the end, reads the production rules, writes some stuff on the end, keeps going. This took about 25 minutes. It doesn't go for 25 minutes now. I compressed time, so it only took... Actually, no, I cut it off. This didn't finish. But when I ran this for real in my Magic the Gathering computer, there it is. It took 25 minutes, and we successfully divided a number by 2. Thank you very much. Round of applause, please. So it turns out that actually the authors of the paper weren't making it up. You can actually make a computer in Magic the Gathering. Problem is, it's really, really slow. And that's actually one of the things I feel like I learned going through this project. Because like, the first thing you ask, if you can write a computer in Magic the Gathering, then can you write Magic the Gathering in Magic the Gathering? And the answer is, well, yeah, theoretically, yes. We may not have enough time left in the universe to run it. And so just sort of the scale of what's going on here, of just how long this stuff takes is it's just obscene to me. Like, I literally left my computer running for days and it couldn't add 1 to a number. You know, it's a lot of computation. But what comes next? Well, so now you're all sitting out there and you're all like, wow, this is so interesting. I want to go out and learn more. I want to do all the things I can about tiny Turing toys. I'm really excited. What comes next? I'm glad you ask. So here are a few different things you may consider. If you're the sort of person who enjoys reading papers, not many of us, but maybe you do. Here is a selection for you. There's obviously the Magic the Gathering Turing Complete paper. Only really makes sense if you know a little bit about Magic the Gathering. But it's kind of fun. Quite like what they've done. Small universal Turing machines. This is the Rogozin paper. This is the one where he dropped like 10 different tiny machines. He's like, I beat you all 10 times. Ha ha ha. Universally of tag systems with P equals 2. That's the one that that shows you how to do the tag production rules. It's actually quite a good read, except there's a mistake in it. I'll let you find it. And there's a really annoying bit where they say, okay, here are the production rules for moving right. And for moving left, it's basically the same. Except it's not. And so I had to figure that out. And I'm still not 100% sure I got it right. But anyway, that's good paper. Make sure you get the 1964 version. They published a version in 1963 that has a second error in it that I was really frustrated by until I found out that I was reading an old version of the paper. So, fun paper, really short. It's only like 4 pages long, quite easy to read. And it was also probably the worst explained of what I did up here. So it's probably a good one to read. Universal Turing machine with 2 internal states. This is the Shannon paper that I didn't actually read, but you know, it's pretty interesting. It's only 3 pages long. Again, him showing that you can make any Turing machine with any number of states and 2 symbols, or any number of symbols and 2 states. Paper where he proved that. Pretty cool. And this paper, bonus paper for you, never before referenced in this talk, called Small Universal Turing Machines by Turlo Neri. I forgot to put the date on it. It's 1990 something. No, it's early 2000s. Early 2000s. This is not just a paper. This is a thesis. It's like 100 pages on small Turing machines, and there's so much cool stuff in there. I'll talk about some of it in a second. So that's really fun. I've barely even scratched the surface of this one, but that's kind of cool too. All right, so those are the papers, if you like papers. But maybe you're more of a book person. Got you covered. Understanding Computation by Tom Stewart. Really fun book, just about this kind of stuff. It doesn't really talk about the same things that I talked about tonight, but it's just a lot of like detailed stuff about computation. I thought it was a really fun read. Maybe you'll enjoy it too. And then Most Human, which is kind of really tangential. The only real link here is that you may have heard of the Turing test about like figuring out whether somebody's an AI. That's really the only link, because Turing, same name, same guy. Maybe you'll like the book. Story time, every year they run a contest, the Turing test contest, where they have computers pretend to be humans by talking to humans. The author of this book says, well, how do I get to be one of the humans? Because there's actually a prize for which, oh no, sorry, I got it wrong. You have a human that the computer's trying to trick, but then you also need your control group human who's trying to trick the human as well, right? So that's like, they're trying to pretend to be a human, and so somebody wins a prize for the most human, which is a human that convinces the most humans that they're human. Great book. It's more of a philosophy sort of book about computation and computers and stuff. So I just want an excuse to tell you about a book I like. But I know, that's a lot of reading. Reading's boring. What do we really want to do? Write code. Great, because you don't need to read any of those papers to write code, though it will help for some of these things. This here is a GitHub repository. It's called Turing Toys. There are lots of Turing toys in there. All of the machines I talked about tonight, there's an implementation in there of them, including the Magic the Gathering one. The Magic the Gathering one's not in Ruby, but all the other ones are. So you can play around. There's a command line tool, there's some examples. It's pretty fun. So, you can go and poke around in there. Some things you could do. You could make your own Turing machine. I made an add 1 at the start. Maybe you want to do an add 2. That'd be fun. Give it a go. You could also just make your own interpreter for Turing machines. It's a really fun sort of kata exercise. Like you sit down and probably bang it out in 30 minutes. Like, okay, I need a tape, I need a read head, I need some if statements. Oh, I've got it. It's still kind of a fun project, right? So maybe you want to make your own thing there. Maybe you want to implement more of Rogozin's machines. So I've got one of them in the repo. You could add the other ones. These are actually really simple. You just need to take his rules and his encoding rules and put them into Ruby code. I haven't done it. You could do it. It's fun. And in theory, you could still, maybe some of them are more efficient. They're not. I know why. I'll talk about that. Maybe you could implement Shannon's algorithm for creating an M2 machine. Because I 100% didn't do this. I totally faked it. So that could be fun. Now here is where things get really, really interesting, I think. So Neary, that's the thesis I told you that I haven't talked about yet. In his thesis, he actually says, oh, well, this thing that Minsky and John did, Minsky and Koch did, was it has exponential performance characteristics, and we don't like that. So here's an alternate system which has polynomial characteristics rather than exponential. So, it provides an exponential improvement in the running time of the Turing machine. So if we did this, and then maybe we did some performance optimizations, because I've literally done none of them, maybe we could get the +1 machine to actually run. Not Magic the Gathering, of course, just, but like we could maybe get there. So in here he talks about there's a couple of different tag systems. There's bi-tags and cyclic tags. There's all sorts of tags. So that could be fun. And if you're actually more interested in Magic the Gathering, there's a heap of to-dos. I've kind of fudged a lot of the steps in that just because I haven't had time to do it. So plenty of options there, from the things you can do in 30 minutes to things you could spend a month on. Maybe some of those are interesting. That's all I've got to say. Thank you very much. I'll hang around for questions if people have them.
Do we have any questions? Anyone? Yeah.
So you divided a number by 2.
Yes. I was going to repeat it, but it's okay. Got it.
You divided the number by 2. What was the number and what was the result?
A good question. I divided 2 and I got 1.
Very good, thank you.
Yeah, good question.
Was it responsive?
Yeah, my terminal is very responsive. Yeah. Worked very well on mobile.
It's good talk. I liked your energy. It was good.
Thank you.
So this sort of stuff, like you did a proof of concept and such.
Yes.
Obviously, they've done that on mainframes and such. They've actually put a lot of computing
So you'd
resources
think,
into these things.
You'd think, but I don't think they have. Because the first question I had was all these computer scientists writing all these Turing machines, and they don't even run programs on them. That's the saddest thing I've ever heard.
Yeah.
I found it really difficult to find any evidence of anybody ever trying to actually run these things. Yeah. They just do the math and they're like, well, that'll do. So, I'm sure somebody has, but I couldn't find it.
Yeah, I was going to ask whether you knew of any cases of anybody writing a functional program, maybe using one of the really fast computational languages or something like that. But if that's not as far as
no, I haven't.
Crazy.
Not in the context of this. I'm sure somebody wrote this is a really fast Turing machine emulator, but then I didn't run anything on it.
Yeah.
I know that people have done this. So you can basically take the same thing and substitute out Turing machines for Game of Life. And I know people have written really fast Game of Life emulators. Game of Life is the one with all the squares that have rules, yeah? And then they've written computers on that and actually run it. So I have a lot of respect for that. So it's also, I feel like this stuff's kind of hard to Google for because you end up getting a lot of random stuff that's not really related. So yeah, if anybody finds anything, I'd love to hear it. Question up front here. Yep.
Thanks. Yeah, so I was confused at the start. You were talking about like how to like make Magic the Gathering
Yes.
into a Turing machine.
Yes.
And then there was a lot of this conversion between like and proofs that there were like these different types of computation machines were mathematically equivalent. So I'm wondering, does this echo what they do in the paper? Like
No.
Okay.
Oh well, so I'll show you exactly what they do in the paper. I just need to. These slides really lag Keynote because they've got 100,000. Oh no, we went too far. So what I want to show you is. Here we go. Ignore that. Nope, escape. I want this slide. Yeah. So what they did in the paper was they said, all right, so we've got this machine, let's encode that into Magic the Gathering. So there was an extra step here with like, imagine arrow, question mark, Magic the Gathering. Right. They did that. That's what the paper says.
So I guess my question is, why did we start with the 2, 3?
Mm-hmm.
Yeah.
Because I said, well, I want to run a Turing machine. So this could be X, Y. Like this could be any arbitrary Turing machine. I just chose this 2, 3, add 1 because adding 1 is cool and maybe resonates with the current zeitgeist.
That makes sense.
Yeah, cool. No other takers? Thank you very much.
I don't know why you need to see the pictures from us, but, why not? More slides. Slides are always good. Use the mic?
No, this is quiet whispering time while we work out where the slides have gone.
Every time.
Don't use the mic.
Don't use Google Slides is probably the takeaway from this whole exercise.
Hey.
Oh, there we go. I don't know how to get them now down here.
Oh.
We'll just have to see if they change. Hey, they changed. That's
Amazing.
exciting.
At some point, this talk will go up as a video on this link here. If you would like to watch it again, it was brilliant. We loved it. Did you get your cards back? Oh, okay.
Literally worthless. But actually, I will.
For your prize.
Sorry, just talking to the mic. I'll also the papers and stuff I put on. I'll post to my Twitter. If you can't wait for the video. So
cool. Thank you. That would be fabulous. Would you like to give a talk? You can do that. We did. It was fun.
Yeah, and we'd be very interested about hearing from anyone who'd like to speak next month. Not right now. Like, I don't want to put anyone on the
You're
spot.
going to have to think about it.
Yeah.
I think, did we strong arm you at Vapiano last month? Or did you offered at Vapiano last month. So
I'll
come.
talk every month. That's all I've got.
So we can hear this again next month, or if you want to talk, please do let us know. If there's a particular talk you'd like to see, for example, if you'd like to see this talk again next month, do go and request it in the GitHub issues.
Or Xavier, you said you had a magic talk as well.
I would do it if people wanted it. But,
If there's a talk you want to see, you can request that here.
You can go to that link and request it. Or it turns out you could tweet us. Apparently.
Yes, that also.
We are on the Twitter.
Yes.
That works. After this meetup, we'll be going some places. Vapiano.
They have cheesecake.
They do. They also have wine if you're interested in wine.
Yep, wine and cheesecake.
And like pasta and more pizza if you didn't have enough, although I think we did.
Please eat more pizza, take some home with you.
There's a few slices left if you'd like some more. And there's also some ice cream to be had. Yeah, we'll be going there.
Yeah, if you're interested in ice cream, you can follow either one of us. We'll probably be together.
We don't get very far apart.
No.
Yeah. Advisable not to get very far apart. Yeah. Thanks for coming. See you next time. You can keep hanging around and talking if you like conversation. That's fine. Thank you very much, Xavier. That's super cool. So many.